In the last video, we defined what a rate was, and then we looked at two examples of a rate. One was kind of a normal example of real life. The other one was a example of a chemical reaction. So now what we're going to do is dig a little bit more deeper. Let's investigate the rate of a chemical reaction. But this time, what we're going to do is take a look at real life data from chemical reactions and see what information we can ascertain from that. Okay, so we're going to look at more detail on the mathematical description of rate. And now the rate of a reaction can give you two pieces of information. One we're going to look at now, and then the other we're going to look at later on in another video. But the one thing that we can take a look at now is the concentration over time. And so that's what we're going to look at now. Eventually, what we're going to start looking at is what's going on at the atomic level. So the rate of a reaction can also give us insight as to what's going on at the atomic level. Okay, and so this is going to be the later part. All right, so we can get information on both of these through something called the rate law. And so this is one of the biggest things that we're going to talk about in this chapter. So we defined the rate in the last video. We said that the rate would be the change in concentration of a component, A, divided by the change in time. Okay, now assuming that the concentration, that A is a reactant, we know that the rate should be going down. So I'm going to say that we're going to put that negative sign there. If the change in concentration is going down, the negative times the negative would give us a positive, so we're good. Okay, so if it's a reactant, we know that should be a negative sign. Now, based on this, we can define a rate law, which is going to be equal to a rate constant, which we give lowercase k to, times the concentration of A, and then A is going to be raised to an exponent power. That exponent is going to be called M. And let's say we have another reactant in the mix. I'm going to call it reactant B. So we have the concentration of reactant B, and this is going to be raised to another exponent power. I'm going to call this N. So again, the brackets indicate concentration. K is called the rate constant. And M and N tell you the reaction order with respect to the species. Now, if you add up the exponents, M plus N, they give you the overall reaction order. And I'll explain the reaction order a little bit later. All right, so now what is the relationship between M and N and its related stoichiometric coefficient? So if you know, let's say the coefficient of A is 2. Does that mean that M would also be 2? Well, we got to be very clear about this. What is the relationship between the exponents and the related stoichiometric coefficient? They could be related. Okay, they could be related, but not necessarily. Okay, so you can't look at a chemical reaction and say, okay, well, if the coefficient's 2, then that means the exponent's 2. It could be that, but it may not be that. So we need more information. Okay, so this is way, 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 way important, everything that we just went over. So let's summarize everything again. Say that about the exponents. Here it is. The value of the exponents must be determined experimentally. All right, so the values of the exponents must be determined experimentally. We cannot assume the stoichiometric coefficient. Okay. Now, how does this make clear by the info in the previous information? Because the rates are constantly changing. All right, so in the next picture, what we're looking at is a graphical representation of an exponent m. So this is kind of giving us some information as to the reaction order. So let's say the rate that let's say that exponent m is 1, okay? And then the concentration of component A is doubled, then that means that the rate doubles. Okay, so we say if the m is 1, then that we say the reaction is first order. Okay, and so if it's first order, if you double the concentration, the rate doubles. All right, now if m is equal to 2, and you do the same thing, you double the concentration of A, what that does is that it increases the rate. It increases the rate by a factor of 4. And so we say that that reaction would be second order. Okay, so you double the concentration, the rate quadruples. All right, now if m is 0, so let's say the exponent is 0, what that means is that if you double the concentration, the rate is going to do whatever it wants. So that means that the rate is independent of the concentration of A. So we say that that reaction would be 0 order. So we'll talk a little bit about that. Now, what if you see a reaction, you see an exponent that's actually a negative number? That means that the rate decreases as the concentration increases. So if you double the concentration of A, it's actually going to be, the rate is actually going to be decreased by a factor of 2. It's going to be cut in half. Okay. Now, to be honest, I'm showing you that it is possible to have a negative exponent, but we're not going to study that in this course. So let's talk a little bit more about what this rate law is. So this is really important for us from a practical perspective as well as a conceptual approach. But before we really study this rate law, we've got to figure out how do we determine this, specifically the exponents, because if they're not tied into the coefficients, then we need a way to determine the exponents. And then also we needed to be able to determine K, the rate constant. Now, there are 3 methods that we can use to determine the exponents and the K, and that gives us the rate law. Okay, so this is actually going to be over a couple more videos. Then I'm going to go into each of the different ways of you can do this. The first method is actually going to be covered in this video. This is the experimental method, and we call this the method of initial rates. Okay, so let's talk a little bit more about this. The method of initial rates goes like this. Okay, we're going to use that initial rate as a primary point. So if we have a generic rate law like this, let's say that the rate, we're going to deal with only one reactant, and we're going to call that reactant A. Okay, so the rate law would be that the rate is equal to the rate constant K times the concentration of our component A, and we're going to raise that to the power of M, and we've got to figure out what M is. Now, if the exponent M is equal to 1, in this case we call that first order. Okay, what that means, again, before we go any further, if the exponent's 1 and it's first order, that means if we double the concentration, the rate should double. Okay, so if the exponent is m equals 1, it's first order, and we compare 2 initial rates, how will the ratio of the rates differ as a function of initial concentration? So in other words, if you double the concentration of A, how does the rate change? Well, we talked about this. I actually just answered this own question. So I said that originally that if you double A, so if A doubles, the rate doubles. Okay. So I said that, and we also said that up here when we were looking at that curve at that bar graph. But now I got to put my money where my mouth is. How do we prove that mathematically? That that's the way it is. That if we double the concentration, that the rate's got to double. So that's what we're going to do next. Let's see how we can analyze this mathematically. So what I'm going to do is to compare two different rates. So I'm going to say, let's say the rate of experiment 2 divided by the rate of experiment 1. And for experiment 2, that's the one that we're going to double the concentration. Okay, so rate 1, that's our normal rate law. So let me write that in. We're going to say for rate 1, that's going to be equal to the rate constant K times the concentration of A, and that's going to be raised to the power of M. Now to keep the A different, make sure that we're keeping everything the same, or a little keep everything straight. What I'm going to do, because we're looking at the bottom reaction, which is the first rate law, for the A, I'm just going to put a subscript 1, just to keep in mind that concentration of A, that's for the first experiment. Okay. Now, what I'm also going to do now, let's write the second rate law, and then this is the one that we double that concentration. So what I'm going to do is write the original, the rate law for the second reaction. So it's the rate constant K times the concentration of A for the second reaction. So I'm going to write 2 as a subscript, and that's going to be raised to the power of M as well. Now, what we're doing, though, is assuming that M is 1. So I'm going to erase those M's, and I'm going to put 1s as the coefficient because that's what we're assuming up there. Okay. Now, we know that we're going to double the second rate, or we're going to double that second concentration. So let's go ahead and do that. So I'm going to double, we're going to double that concentration of in the second reaction. So I'm going to write 2 of A1 because we're doubling the concentration of the original reaction times K. And then in the first one, it's still the same. K, the rate constant K, times concentration of A from the first reaction. And then, of course, these exponents are still 1. Okay. So let's see what we can do. If we still have A, that means K still has to be the same. So these K's will cancel out. Okay. And a concentration of A1, that also stayed the same. And so the only difference is everything on the bottom drops out to be 1. The only thing left on top is your 2. And look at that. It's a ratio of 2 to 1. So if the concentration is doubled, the rate has to double. How cool is it that the math is actually telling the story here? But yeah, so this is extremely straightforward. This simple analysis is very useful because now what we could do is use this as a model to solve a chemical problem. So let's try that. Okay, so here's our problem. The reaction of study is going to be 2 moles of NO plus 1 mole of Br2 yields 2 moles of NOBr. Okay, and here's a set of data for the initial rate at various concentrations. Determine the rate law of this reaction. All right, so it looks like we've got 5 different experiments. Okay, so we're looking at the initial concentration of NO and the initial concentration of Br2, and then looking at the initial rate of formation of NOBr. So for instance, for experiment 1, we are keeping the concentration of NO at 0.1 molar. concentration of Br2 is 0.1 molar, and the rate of formation is 12 molar per second. Okay. Experiment 2, we double the concentration of Br2. So I'm going to write 2x here. Okay. If we double the concentration of Br2, the rate seemed to double. Okay. For experiment 3, we go from having a concentration of 0.1 molar Br2, now it's 0.3. So we tripled this, and it looks like the rate of formation also tripled. So I'm just trying to figure out I'm just trying to, eyeball these and see how these go. Now, just a heads up, are the numbers, when we do these calculations, when we do these problems, are they going to be perfect like this? No, absolutely not. This is a good example, though. We're just eyeballing it, taking a look at it. I'm going to show you how to do this mathematically, so that way, when you do have one that has really ugly numbers, it's not so bad. All right, so let's take a look. Experiment 4. We're going back to the initial Br concentration of 0.1 molar, back from experiment 1. And in experiment 4, we're doubling the concentration of NO. Okay, so let me write 2x here. And it looks like, look at what happened. The rate of experiment 4 compared to experiment 1, that's like that is definitely 4 times as fast. Okay, and then experiment 5, it looks like we're tripling the concentration of NO, and we're keeping the concentration of Br2 the same. And now it says predict. Okay, so we got a lot of stuff going on here, and it looks like we've got some other questions that we've got to answer. So let's figure this out. Now, I'm going to be honest with you. When I wrote this up, I did not really give myself a whole lot of room to write these answers out. So what I'm going to do is to get a sheet of paper. So let's see if I can add this to my notebook. Let's see if I can add a sheet of paper here. And we are on page 61. So let me see if I can add a page. There we go. All right. So what I'm going to do here, let's get some data. Okay. Let's get some data. So we wanted looking at this table. Everything is kind of hinging on experiment 1. This is our baseline. Okay, so everything is being compared back to experiment 1. So what I'm gonna do is write that again. So for experiment 1, the concentration of NO was 0.1 molar. The concentration of Br2 was 0.1 molar. And then the rate was 12 molar per second. Okay. Now what we want to do is compare experiment 1 to something else. We want to compare experiment 1 to another experiment, but here's the deal. We want to double the concentration of one of these and keep the other the same. So for instance, if we're going to go after the concentration of Br2, let's say we want to find that exponent. I want to double the concentration of Br2 and keep the initial concentration of NO the same. So in this sense, we could take a look at experiment 2 and compare that to experiment 1. All right, so let's do that. So I'm going to write out the data for experiment 2. The concentration of NO in that experiment is 0.10 molar. Concentration of Br2 is 0.20 molar, and then the rate was 24 molar per second. All right, so now what we're going to do is pretty much what we did in the last problem. I want to write a rate law of experiment 2 over experiment 1. So I want to get a ratio of the rates. So I'm going to say that the rate of experiment 2 divided by the rate of experiment 1. 1 goes on the bottom because that's our baseline. So the baseline for experiment 1 was that we have the rate law K times the concentration of NO raised to the power of M times the concentration of Br2 raised to the power of N. We don't know M and N for this problem. The last time we did this, we assumed it was 1. Okay? In here, we can't assume that. So we've got to figure out mathematically what's m and what's n. So what we're going to do is go after n first, solve for that, and then we'll figure out m. Okay. Now what I'm going to do is write the rate law for experiment 2, which is going to be the rate constant k times the concentration of NO raised to the power of m times the concentration of Br2 raised to the power of n. All right, so we got some information now. We know that the concentration for K, if we go down to rate law 1, we don't know K yet, but the concentration of NO in that experiment was 0.10 molar. Concentration of Br2 in that experiment was 0.10 molar. If I write out experiment 2 now, rate constant is still K. We don't know that yet. Concentration of NO was 0.10 molar. Concentration of Br2 was 0.20 molar. Okay. And the exponents, I forgot to put those in, so let me put those in. M, N, N, N. Okay. And this, let me see if I can close this up. I'm going to write this is going to be equal to the rates. The rate for the second reaction was 24 molar per second. The rate for the first one was 12 molar per second. All right. Okay. Now, notice what happens here. If we take a look at this, you've got the rate constant. It's K. We don't know what K is, but you've got one on the top and the bottom. So they would cancel each other out. You've got 0.10 molar raised to the power of m. You got 0.10 molar raised to the power m on the bottom. Those two cancel out. So now you're left with this. You're left with a new fraction. So let me rewrite what we got. We got 0.20 molar raised to the power of n divided by 0.10 molar raised to the power of n. This is equal to 24 divided by 12. Now we can simplify this a little bit more. Okay, so if we were to combine a whole, the left-hand side into one expression, what that would be is something like this, where you have 0.20 divided by 0.10 divided raised to the power of n. This is equal to 24 divided by 12. Now, 0.2 divided by 0.1 should give you 2. So 2 raised to the power of n is going to be equal to 24 divided by 12. Well, that's also 2. Okay, so 2 raised to the power of n has to be 2. So that being said, n, looking at this, n's got to be 1. That's the only thing n could be in order to make both sides the same. All right, so that's all well and good, but what if you had to solve for that exponent? Because I'm going to give you a problem that you're going to have to do this. All right, so let me erase what I just did for the n. What we're going to do is use the laws of exponents to get the n down. So I want to figure out what n is. So in order to get that, to rewrite this, what I'm going to do is convert 2 raised to the power of n. I'm going to write that as a logarithm. So if I convert this to this left-hand side to a logarithm, what that would be, we would be taking n times the log of 2. So the 2 would be your base. The exponent would be multiplied by the log of 2. All right. Now, since we converted that number to a logarithm, we also have to convert the right-hand side to a logarithm. So that would be the log of 2 as well. Okay. All right. So now we got to get n by itself. So we're going to divide both sides by the log of 2. Okay. If we divide both sides by the log of 2, look at that. Log of 2 divided by log of 2 is going to give you 1. That means n's got to be 1. And there you go. So that's how we know what the first exponent is going to be. Okay. Now, what we need to do, now that we know n, we've got to solve m. So now what we're going to do is go back to that experiment. Now it doesn't quite matter what the concentration of Br2 is because we know that exponent. Now we want to look at an experiment where ideally we're doubling the concentration of NO, but we're keeping the concentration of Br2 the same as experiment 1. So that would be experiment 4. We double the concentration of NO, keep the initial concentration of Br2 the same, and then look at that rate. All right, so let me write that information out. So we're going to, the rate of experiment 4, the rate of that reaction was 48 molar per second. Concentration of NO is 0.20 molar. Concentration of Br2 is 0.10 molar. Okay, and that's again coming right from that table for experiment 4. So we're going to write the rate law for experiment 4 comparing experiment 1. Again, this time rate of experiment 4 is going to be on the top. The rate of experiment 1 is going to be on the bottom. Okay, so this is going to be equal to the rate constant K times the concentration of NO raised to the m power times the concentration of Br2 raised to the first power. We're going to do the same thing for the experiment 4. K times concentration of NO raised to the m times the concentration of Br2 raised to the first. All right, so we're going to pop in those values now. So we still don't know K. We're going to get there eventually. K times the concentration of NO for this experiment is 0.20 molar raised to the m power times the concentration of Br2, which is 0.10 molar raised to the first power. And then we're going to pop in our numbers for experiment 1. We got 0.10 molar for 0.10 molar for NO, and then we got 0.10 molar for Br2, and 0.10 molar for NO is raised to the m power. For Br2, that's raised to the first. And this is going to be equal to the rate of the fourth reaction, 48 molar per second, divided by the rate of the first reaction, which is 12 molar per second. All right, so let's see what we got. Let's see what we got. And I'm starting to run out of pages again, so let me add another page to this. Perfect. All right. So what cancels out? The K's cancel out again. The BR actually cancel out again because those are the same. So we're getting 0.20 raised to the m power divided by 0.10 raised to the m power. That's equal to, and these are all in brackets, this is all equal to 48 divided by 12. Okay. So if I wanted to write that 0.20 raised to the m divided by 0.10 raised to the m, I could write that as a fraction. That would be 0.20 divided by 0.10 raised to the m power, and that would be equal to 48 divided by 12. 0.20 divided by 0.10, that would be 2 raised to the m power is equal to 48 divided by 12, or 4. Okay. All right, so you can see where this is going. What 2 raised to the what power is going to give you 4? Well, it's got to be 2, but let's use the law of logarithms to help us get to that. So if I convert the left-hand side to a logarithm, I'm going to take m times the log of 2 is equal to the log of 4. If I divide both sides by the log of 2, so I get m by itself, I get log of 2 cancels out. So on the left-hand side, so we get m is equal to, we have the log of 4 divided by the log of 2. So that would give you 2. So the second exponent has to be 2. All right. So that's how you would determine the exponents for that reaction. All right. So let's check out some of the answers on these questions. So let's go back to the worksheet, the questions so far. So the first question says, which experiments will allow you to determine the order with respect to NO? We used experiment 4 versus experiment 1. Okay. Which experiments will allow you to determine the order with respect to BR2? We used experiment 2 versus experiment 1. Okay. Which experiment will allow you to confirm the order with respect to NO? So this one's a good question. Which experiment will allow you to confirm the order with respect to NO? Well, we would, if we know, ideally, experiment 3 and 5 would be able to give us that information, ideally. All right, so this one we can't answer quite yet. We need a little bit more information, but the next question goes like this. Predict the initial rate for experiment 5. We can't answer this one quite yet either because in order to answer this, we need K. And we don't know what K is. Okay, so let's not get there yet. But let's go back to our problem. So we just solved for the exponent. What I'm going to do now is solve for K. And in order to solve for K, we're going to focus on one experiment. So let's use experiment 1. Okay. So again, the concentration of NO was 0.10 molar. Concentration of Br2 was 0.10 molar. And then the rate was 12 molar per second. Okay, so that's what we know. All right, so what we're going to do is pop in those values into our rate law. So rate is equal to K times the concentration of NO, which is raised to the second power, times the concentration of Br2 raised to the first power. Now the rate was 12 molar per second. We don't know K, but we know that the concentration of NO was 0.10 molar, and that's going to be squared. And the concentration of Br2 is going to be 0.10 molar, and that's going to be raised to the first power. All right. So we're now going to solve for K. So in order to get K by itself, we're going to have to divide both sides by the concentrations of both species. So I need to divide both sides by the concentration of 0.10 molar raised to the second power times the concentration of 0.10 molar raised to the first power. And so that's going to go on the left-hand side. 0.10 raised to the second times 0.10 raised to the first. So that way, K is completely by itself. All right. All right, so if we've got 0.10 squared, that value, I'm going to rewrite this over here, 12 divided by 0.10 squared, that would be 0.01. And then you're multiplying, you're raising 0.10 to the first power, so that's still 0.10. So if you multiply these two together, this actually should come out to be 12 divided by 0.001. Okay? And when you take those two, that should give you 12,000. So K should be equal to 12,000. Now, this is the important part. We've got to figure out the units. All right, so look, you got this. You know molar per second for 12. For the 0.01, that was going to be, let's write I'm going to rewrite this with the units now. 0.01 molar squared, because we squared that one. And then for the other one, it was 0.10 molar. So molar squared times molar, that would give molar to the -3. Molar raised to the third. For the top, it's molar per second. So molar divided by molar raised to the third power, that's actually going to be molar to the -2. and then second to the minus first. And there you go. That is the unit. That's your rate constant and the unit for K. All right, so now we know what K is. So if I go back up here, okay, if I go back up here, I'm actually know what this rate law is. The rate law would be rate equal K times the concentration of NO raised to the second power times concentration of Br2 raised to the first power. All right. And we know, so we got the rate law. We can actually solve for that rate constant, which is what we actually just did. We know that the rate constant is 12,000 molar to the minus second, second to the minus first. Okay. Now, what we need to do, since we got those values, we have to go back and solve for the initial rate for experiment 5, the rate that was missing. So let's do that. Now, in experiment 5, concentration of NO was, let me look that up in my table. Concentration of NO was 0.30 molar. Concentration of Br2 was 0.10 molar. And the rate, we don't know. That's what we're solving for. But we do know the rate constant now. So if I write a rate law, rate would be equal to the rate constant K times the concentration of NO raised to the second times the concentration of Br2 raised to the first. If I pop in the concentrations and the rate constant, so the rate constant we know is 12,000 molar to the minus 2 second to the minus first times the concentration of NO, which is 0.30 molar raised to the second power, times the concentration of Br2, which is 0.10 molar raised to the first. Okay. So now I just have to solve for the rate. Okay, so if I do that, if I take 12,000 and then multiply these out, these should give, the rate should be 108 molar per second. So what should happen is that when you have molars and you square it, that unit should cancel out with a molar second, molar to the minus second. You still have a molar over here, so it's going to give you molar per second. But yeah, that's going to be the unit. So what is that the rate for experiment 5? 108 molar per second. So we can go over here, predict the initial rate. Now we know 108 molar per second. Cool. All right, and that's how you solve a method of initial rates problem.